folks. Okay, let's just see if we can make some headway into this chapter 6 here. This is substitution and elimination. All right, so where we ended off last time, where we began talking about the mechanisms and the differences of the mechanisms between SN1 and SN2 reactions. So this is a good place to start here. All right, so for SN1 reactions, you know, this is a stepwise process. Unlike SN2 reactions, which is more of a concerted process, like one thing happens, one collision happens, and then in that collision for SN2, you have the incoming nucleophile, which helps to displace the leaving group. Okay, and so that happens all at once. In SN1 process, it's a little bit more complicated, a little bit steppier. And it's not too bad though, all right. But you'll see. But by the end of the chapter, you'll see that, these mechanisms are, they seem complicated in the very beginning because we talk about the Gibbs free energy and so forth and so on too. But as we talk about the rest of organic chemistry, pretty much every mechanism falls into these basic either 2 or 4 mechanistic categories, depending on how you think of them, either as a concerted process or as a stepwise process. All right, so that's how we can think about it. Okay, so let's just get right into it. Okay, so for SN1, the first step in an SN1 process, and we'll talk about what makes a good SN1 process, but let's just talk about the mechanism first. What first happens here is that you have a, I'll try and draw if I can on this machine draw. Okay, what first makes a good, this is my pen. All right, what first makes a good thing to draw here, a good thing to react here is, you have to have a good leaving group. And we talked a little bit about what makes a good leaving group, which is either going to be some stability through an ion that could be, stabilized by the solvent, or with a leaving group that has some nice resonance associated with it. In the case here, we have a alkyl halide here, which then, when it ionizes, when it leaves, it gives you the Br minus ion, again, which is a nice stable ion in and of itself. This is the rate determining step because it is the slow step. All right, so this is the first step in an SN1 process. All right, so let us go into here. All right, and so the first thing happens is that you go from your substrate to your transition state, and your transition state here is the thing that we just talked about, your ionization process, your rate determining step. This is the delta G1, right, which is your first ionization process. Then you end up going down into that slope to make your intermediate, right? And your intermediate here is your carbocation that is formed after the leaving group leaves. Okay, this is your carbocation. All right, and then after this happens, and so there's two ionic intermediates. There is the carbocation intermediate in the case of an SN1 or an E1 process, and in the case of an SN1 process, there's the incoming nucleophile's first form, first bond that is formed, right? And then that also is an ion that has to be dealt with, which we'll show you how to do. Okay. So here's where our first step is. We have this tertiary carbocation, and then that tertiary carbocation has a certain level of stability, which is why it is on a local minima. All right, and that local minima is an important thing to be able to determine if you actually have it, or what makes a good intermediate carbocation, right? And we'll talk about that. What makes a good, how can we stabilize that carbocation to form that? All right. And so after that, then we have the transition state 2, right, which is after the tertiary carbocation, right? And then that happens just before this step here. So here's your tertiary carbocation, right? And what happens there is that then your water attacks in here, because we're using, in this case, the hydrolysis of a tertiary of a terpial bromide. So after water attacks, you have this hydronium ion species. And this hydronium ion species here is a stable species, sort of stable species, because you have another sigma bond that just formed, but now you have this oxygen which has a positive charge on it, and oxygen does not necessarily want to have a positive charge on it, it being very electronegative. So we have to somehow deal with that positive charge in some way. All right. And so now we are at the second intermediate step, all right? So in a way we have to somehow get rid of this this intermediate, right? And he's like, well, listen, it's stable, so why don't you just leave it alone? Well, it is stable, but it has the sense that it could be even more stable if it does some minor things, right? If it goes to the leftward, if it goes back up to that transition state 2, well, that's a higher energy process. All right, but if it keeps on going rightward and it heads down towards the transition state, the TS3 here, right? You have a chance in this thing here being, ultimately getting to its final resting state of having the tertiary alcohol. All right. So even though you have to pay a little bit of price in terms of Gibbs, in terms of Gibbs free energy and some activation, in that ultimately you are getting all that back after you form your final product, right? And that final step is not that bad, right? So in step 3 here, you have this water that comes in and abstracts this proton from this hydronium species over here, right? And that's all well and good. You can do that, and it's not that big a deal. Yes, you pay some energy price, but that price is not too high, actually. And that is also, again, a fast step. Your only slow step here, as you can remember, right, is your initial ionization of your first process, right? The ionization of the bromide to give you your tertiary carbocation. All right. And then, once your final abstraction, your final proton abstraction occurs, then you have your final product, which is your tert-butyl alcohol, tert-butanol, that is. All right. And so this is your overall situation. You are now completed with your reaction of your SN1 diagram. Now this diagram here, I would say, is a sort of a semi-simple SN1 diagram. You can have diagrams that are much more complicated than this based on what your carbocation is or what you form. You could have carbocations that you form that might be sort of stable, but they might want to rearrange into other stabilized species, which is something that we will get into in just a little bit. All right. And so in terms of this here, here's our step 2 and step 3, and here's where the where our rates really sort of come in a little bit when you want to talk about them. Your K1 is much slower than your K2 and K3. These are fast steps here. Your K1, your first thing that happened is your ionization process. So that is your rate determining step. We won't necessarily talk about numbers here, right? We will talk about relative rates, but that's about it. The only time we'll talk about numbers is in bond making and bond breaking in terms of enthalpy of formation and so forth. But for right now, we won't talk about any other like rate values. Okay. This specific one here, this specific reaction that we talked about here has 2 intermediates and 3 transition states. Like I said in class, I'm going to go back to this. Transition states will always be on local maxima, and intermediates will always be on local minima. Now they will not be on absolute minima, right? Intermediates will be on relative minima. The absolute minima will be the starting material here, on your left, and then your final product there on your right. But your intermediates will be on local minima. So they'll be on the dips. They'll be on the troughs, as it were, right? But your transition states here will be on the maxima of each of these things here. And please don't get it in your head that for SN1, you always have to have two intermediates and 3 transition states. No, you'll more or less always have more transition states than you have intermediates by about 1, but that's about it. But there's no golden like 2 or 3, like 2 intermediates and 3 transition states. It's only for like this specific example. All right, but chances are, for the most part, you will have you'll have more transition states, right, then you will have intermediates. You sort of almost have to, right, because you have lots of for every mountain you climb, you have to sort of slide down that mountain, right, and then ultimately when you slide down that mountain, you're sliding down your last slide should be to your final product. Okay, all right. Here's the one thing that's sort of like really super important about intermediates in these SN1 and in the case very shortly E1 processes. These are the carbocations. So the carbocations have a trigonoplanar arrangement, and that's something that we've known for a little bit. And the reason why they are a trigonoplanar arrangement is because you have your available p orbital that exists above and below the plane of the carbocation, as evidenced by this cartoon right over here. There's potential electron density above and below, which is sort of flattening out the three things around this carbocation. Just so happens this is the ideal carbocation. It's a tertiary carbocation. If you had other carbocations, it would still adopt a trigonal planar arrangement, but the methyls really highlight the fact that it is a triangle that you are forming. All right. When this guy here forms, this means that if this was, and in this case it would have never have been, but if this carbocation came from a carbon that had a leaving group that had some stereochemistry on it, that means that when you form your carbocation, you would have lost all of your stereochemical information, and that is a super important thing to know. All right, the general order of reactivity towards SN1 reactions is the presence of the ability to form an effective carbocation, and the more stable the carbocation, the faster the SN1 process. So tertiary is the highest order of reactivity. Then after that comes secondary. Then come after then way far down the road is a primary carbocation, which almost never forms, and then methyl pretty much almost never forms at all. We have these like greater than, less than, symbols here, but really tertiary carbocations form readily. Secondaries also form pretty readily depending on what they are. Primaries almost never form, and methyls never form. But I say never because I'm a human. In science, there's never a never. There's always it's greater than 99%, but there's always a 0.1% that you could never use on your exam that would make this an argument. So for in our heads, let's keep it in our heads that tertiary form, secondary form, and then primary and methyl almost never form. All right, so there's that. And there are good reasons for these things too. And so when I come in next time, I'll draw these things out for you during lecture, because I have a much better way to look at this. But here is, through positive inductive effect, we've talked about induction before. If you have alkyl groups in a tertiary carbocation situation, these alkyl groups here all donate electron density from the alkyl group to the carbocation, right? And it just goes to show here that the more R groups that you have surrounding the carbocation, the more those groups here can stabilize that carbocation. Or the way to look at it in the opposite way, the more help, the more stabilization can be received from the carbocation, from the alkyl groups to the carbocation. The carbocation here can get more help because it has more alkyl groups around it. Right? And if you have fewer groups around it to help with the electron density, it will be less stable. Here you have, on your leftmost, you have three R groups being able to stabilize this carbocation. So going to the right, you have two R groups here that can stabilize this carbocation. And then as you go down here, you have one, and then you have none here as you go further down here. But 3 and 2, your tertiary and your secondary are your main things that you have to be able to stabilize your carbocation. Now the book uses the term inductive effect, and that's absolutely what it is, but we know this as another word, and we may have used it already, and that word is called hyperconjugation. Hyperconjugation is also is another way to express this positive inductive effect. And hyperconjugation is essentially the ability to transfer some electron density from one side of the bond, from the electron pair, to the other side here, using a network, right? And we talked about this a little bit before, and I drew these really like super crude structures before. I'll see if I can re-sketch it out here too. If you talk about these, the carbon like this, right, and then you have like this guy over here, right, that has a hydrogen on it here. And I'm going to draw hydrogens on these guys here because it's like sort of important to have some hydrogen, because one thing you want to be able to have when you have hyperconjugation is our polarizable bonds. And if you have some hydrogens on your carbons that are neighboring, right, those hydrogens are really great at being polar covalent. All right. And so I'm going to draw here is this and this and this. All right. And so what we said before is that if you have hyperconjugation, each one of these hydrogens around that, okay, I'm sorry, the carbocation right here. Each hydrogen around the neighboring carbon have polar covalent bonds, which means that the electron density will be a little bit chubbier towards the carbon because it's more electronegative, and towards the carbon they'll be a little bit more slender. And that happens pretty much in all the cases around a tertiary carbocation, right? Again, it's just better to have hydrogens on your carbons that surround the carbocation, right? But you don't necessarily have to have that, but it helps. It just helps. All right, so make sure all these bonds here that are hydrogens, that their bonds here are chubbier towards the carbon and more slender, right, towards the hydrogen. I'm making a complete mess, and I think this is a really unfortunate choice in color that I used to draw because it looks a little bit, well, we won't go into it. All right, make this a little bit fatter, a little bit slender. All right, I'm sorry, it's not. I don't have a lot of space to draw here. Okay. When I come in next time, I'll draw it better for you, okay? And because these carbons here have a polarizable situation going on here, what you can have here now is that all this electron density that is around these carbons here cannot transfer this extra electron density down in through this bond over here and forming these bonds here towards these carbons, towards this carbon here as being a little bit chubbier. That's gonna be the name of my organic chemistry textbook. Chubby carbon, chubby electron pairs. That's something for the person who tries to kill themselves with food. There's that. Okay. All right. So now I'm making the bonds towards the carbon a little bit chubbier versus the ones that are further away. I think that should be a drinking game for you guys. Like replay these videos after you graduate from my class, and every time I say chubby, you should just drink. That's a good drinking game. That's, by the way, I'm not endorsing it. I'm just suggesting it. That's two different words. All right. So I'm not saying you should drink. I'm just saying it might be fun, or not. It could not be fun at all. All right. So now I have all this extra electron density around the carbon, and there you go. There you have it. All right. So now you have some partial. You have some delta. Hey, I can draw a delta minus around this. These carbons here. This carbon. I'm going crazy. Oh, I could back up. I know how to do this. Zoom out. There you go. Don't go crazy. All right. This guy here, right, can be, that guy there is going to be around here. This guy here will be a delta. Let me erase. Oh, I erased the whole stupid thing. I can't go backwards. Please try to remember that I didn't mean to erase the entire stupid thing. Ugh, such a schmuck. All right, let's just say this. All right, doing it up here. All right, there. There. All right. This partial delta negative 3 times over in the case of the tertiaries will help to stabilize that carbocation. And when you have a situation where the R group here has some hydrogens on it, and those also have this situation where you have, that stabilization of that electron density, and then that electron density gets transferred through the carbon there, and then into the bonding electron pair there. You have something called hyperconjugation, which we brought up before. So hyperconjugation. All right, hyperconjugation. And hyperconjugation is another word for the inductive effect of that is the reason why tertiary and secondary carbocations are much more stable than what would be the theoretical primary and methyl carbocations, because you have more electron density that can be transferred inductively through a conjugation type of an effect, right, to be able to stabilize that carbocation. That's all it means. That's all that means. All right? Okay. All right. Let's go to the next thing. Okay. So here's sort of the implication of what we're talking about. So if you have the unfortunate situation where, your leaving group is on a, is on a stereo center, well, then you have the situation where, this guy here leaves, and, in the case of, this tertiary bromide species, this guy here leaves. Your incoming nucleophile will be your methanol in this case here, but your first intermediate is going to be this trigonal planar carbocation, which is a tertiary carbocation. Not only is it tertiary, but it's like wicked great tertiary. It's not just a tertiary because of the methyl, ethyl, and the phenyl. This phenyl also has a wonderful benzylic portion, to this, a benzylic part to this, which we didn't talk about here yet. All right. So this guy here is called a benzylic carbocation. This benzylic carbocation, this guy here looks like a primary carbocation because it's a carbocation that is on a singular carbon, right, with two hydrogens on it. But don't let this fool you. This is the highly prized benzylic carbocation. And benzylic carbocations are super duper stable because this carbocation here, while it might look to you like it might be a primary, actually is super stabilized throughout the entire benzene ring. And that is crazy great, right? Because remember back to resonance, right? The more resonance structures you can draw, the more stable the overall product is. You can draw this resonance canonical form, plus if you push this guy here from here, I'll just see if I can draw it from there up to there, forming that guy there, forming now this carbocation, and imagine then drawing that to go from there to there, forming the carbocation up there, and then so forth and so on all the way around the ring. You can draw 4 canonical forms of this carbocation. That's fantastic. All right, and less so, but still pretty awesome, is an allylic carbocation. Again, it looks like a primary. It looks like a primary, but it is not a primary because you can draw some resonance structures that make it an ultra stabilized species. Not only will you have that carbocation, but you'll have the other carbocation based on its resonance structure. And again, this is only with allene. Imagine if this is a more of a complicated structure. As long as you have the allyl features within that chain, then you can have all the benefits of the allyl group while having it be a regular molecule, right? And in the case here of this benzene species here, right? This benzylic carbocation could be part of a much larger structure. Imagine if you put another carbon off of this benzylic carbon, then you have not only a benzylic carbocation, but whatever this would be normally. Like maybe this would be not only this guy here could be a tertiary carbocation, like the next example, right? Like the next example. So let's go into that. So here's your next example of. So now you have this tertiary bromide here, which then the bromide leaves because it's an SN1 process. Now you have this crazy tertiary carbocation, which is also a benzylic carbocation, so super stable, right? And then you have methanol that comes in and will attack that carbocation to give you this racemic mixture of this ether, right? Why is it a racemic mixture? Well, because your carbocation that you formed is a trigonal plane. It is a trigonal planar arrangement. So if it's a trigonal planar arrangement, then it's going to have, then there's no reason, there's no bias that the methanol should come either from this side of the carbocation, from this side of the trigonal plane, or the other side of the trigonal plane. And so that's the reason why you have essentially a racemic mixture whenever you have your leaving group that is also a stereocenter. So here we have this S stereocenter here, and once this guy here leaves, all this S information has now left, right? So then your trigonal plane can be attacked from either this side here or the other side there to give you a 1-to-1, a 50-50 chance of R or S. But because you have a 50-50 chance, it means that pretty much you will get a 1-to-1 mixture, which means that your mixture will be an achiral mixture. You'll have race mates. You will have one measure of R, and you'll have an equivalent measure of the S. All right. So that's a thing that happens all the time. All right. Here's the case here. Now here you have an SN1 process on a secondary position. Again, not as wonderful, not as readily occurring as the as the benzylic and tertiary position thing, but you can still have it, right? So here you have your bromide here, which is the R-bromobutane. This guy here leaves in the slow rate determining step. You're going to have your water, because there's your nucleophile being water. Your water can attack either from the top face or the bottom face. If it attacks from the top face, it gives you this species over here, this R species here. If it attacks from the bottom face, it gives you this hydronium species here, which then gets deprotonated to give you this S species over there, to give you the one-to-one racemic mixture. So if this was a situation where you had a much stronger nucleophile, if this was a hydroxyl, right, for example, you would go from the R bromobutane to the S butanol. But in this case here, you don't. You have the SN1. The SN1 gives you a one-to-one mixture of the race mates, right, of the R and both the S. So here's yet another example of this, right? But this one here now has, this guy here is not a stereocenter. There's no. It looks like there might be a stereocenter, but there's actually not, because if this is the guy that we're talking about, this iodine here is something different. That methyl something different, but these two CH2s and CH2s, if you follow them all the way down, goes to CH2, CH2, then the CH2, CH2, then they both meet at the tertiary tertiary butyl group here. So it looks like it's a stereocenter, but it's totally not a stereocenter. So here's the other example where you have the iodine leaving, rate determining step. The methyl not going to attack from either the top face or the bottom face, and it will give you this guy here versus the other guy here. Now, in this case here, this is a very strange case, because I submit to you, come on, stop it. Do not anger me. Okay. Because here, I submit to you that these two guys here are not necessarily equivalent in terms of energies. Here, there's no question that the R and the S alcohols are equivalent in energy, right? Because they're simple molecules. They're just simple chains. Here, I am not convinced. So that's why I said before, like in our last class, I said, for the most part, when you do an SN1 reaction, you will have a racemic mixture, okay? But unless there's some other external force acting on that addition, and this might be the case here. This tert-butyl group here, this humongous group here over here at the end of the ring, is a gigantic group which will keep this ring here locked into this chair, this specific chair position. Because remember, like, the whenever you have a tert-butyl group on your cyclohexane ring, it pretty much locks the ring into whatever is going to put the tert-butyl in the equatorial position, pretty much to about like 10,000 to 1. I submit to you that the O methyl here versus the methyl here have two different steric costs. Like I say that the O methoxy here is a larger group overall than the methyl here is. So maybe my guess, if I had to guess here, between these two and these two not enantiomers, these two isomers, I would say that this O-methoxy, this methyl here, will probably be a little bit more in excess than this methoxy here on the left. So this methoxy here on the left would be a little bit less so than this methyl here on the right, because the methyl here is a smaller group to put in the axial position. So that would be my guess. So let's argue about it if you want next time you see me. But I'm gonna, if I was a betting man, that's what I would bet. Okay, just because the steric cost of the methoxy versus the methyl, there's less steric cost for the methyl being axial than the methoxy being axial, and one of them has to be axial. So there you go. All right. Factors affecting SN1, SN2, the substrate of the structure of the substrate, the concentrations, of course, for SN2 reactions, the effect of the solvent, that's more important for SN1 reactions, and the nature of the leaving group. Is it a good leaving group? If it's a great leaving group, then it's going to be more favored towards SN1. So the effect of the substrate, of the structure of the substrate here is, in terms of reactivity towards SN2. Methyl will be the most reactive, followed by primary, and then secondary and tertiary, vinyl and aryl, do not undergo SN2 reactions, period, end of statement. Why? Well, for vinyl and aryl, the energy is just not there to overcome the energy of the sigma bond and the pi bond. So that's the thing. But for tertiary, it's just too sterically encumbered. You can't, remember for an SN2 reaction, you have to have the ability for the nucleophile to come in from the backside to displace the leaving group. The nucleophile cannot get in behind a tertiary substrate in any way, shape, or form. So that's just not going to happen. But it can definitely happen, but for a methyl thing, or primary or a secondary, and even a secondary is borderline. But for tertiary, no way, Jose. All right. All right, and so, and again, here's again just some data for you. All right, so the most reactive is a methyl, the least reactive is a tertbutyl here. And, again, the nucleophile here can come in behind this methyl group over here and kick off the bromide. In the case of a primary species here, the nucleophile can come in and attack into that CH2 here and kick that off. But it'll have to do with a little bit of aggravation, with that methyl group here, which is why it's 2 orders of magnitude roughly less quick. Now going from a primary to a secondary, look at this. It goes from 4 times 10 to the 4th to 500 in just terms of just relative reactivity. This guy here, this secondary over here is going to be again, pretty starkly hindered because the hydroxyl in the case here has to get in between that methyl and that methyl to hit that carbon over there to have the bromine here come on off, and then that's not going to happen because again the hydroxyl has to squeeze in between the two methyls. Here's a case here which I think is a pretty, it seems really specific, but it's a really good case here, right? And let me just go to the drawing thing if I can. See how badly I can screw up this slide. Okay, so here you have, here's your hydroxyls have to come in the back behind this guy here, tap that guy there, kick this off here, and there you go. There's your secondary hydroxyl species, isopropyl alcohol. But in the case here, just look at the scenario, and again, please do out these mechanisms yourself. This hydroxyl species has to come in behind, not this carbon, but this carbon right over here. So it's still, it's still technically a primary carbon. Oh, cut it out. Sorry. Zoom up. I'm not going to try to erase that because every time I erase something, it's going to erase the whole stupid slide. All right. So if this hydroxyl attacks the backside of that carbon here, it breaks up this guy over here. But this guy here is like super slow. But you say it's a primary, yeah, but you just can't live that way. You can't say it's a primary, so it's so fast. It should be like this fast, right? And it's not. Why? Because you are right next to you're right next to a quaternary carbon, and that quaternary carbon is going to give it a lot of aggravation in terms of sterics. So even though it's a primary, you can't live in a vacuum. You just can't be like, well, primary and super fast. No, primary here is super slow because of the effect of the substrate, the bulkiness of the substrate. But you still have a shot. You have a shot, right? And so that's why it's 1. It's crazy. It's ultimately unreactive, but theoretically you can have 1. But don't ever try and pull this on an exam. It's still going to be wrong. Whenever I ask you for like a reaction mechanism or a synthesis, I'm going to expect that you can at least get, 15-20% yield on your product. You can't convince anybody getting a tenth of a percent of a yield and have that what you would call a successful reaction. So please don't even try that. All right, and here is the case here where you have a tertiary substrate. You can't, like the hydroxyl here, physically can't even get in behind there because these guys here offer, and you remember that funny little graphic, offers all kinds of crazy steric hindrance. You can't get past those two bulky guys to get in to kick off that bromine. Still though, we still say it's like less than 1. We don't say it's 0 because we're afraid of anything that's absolute. So it's going to be less than 1. It'll be so slow and so unreactive as to be essentially non-existent. That's what it's really saying. That's what we're really saying there. Okay. Okay. So Cut it out. Cut it out. Don't. All right. All right. And so here's like a few situations here to compare. Just to methyl versus methyl versus a secondary. You can look for yourself on that. Here's your methyl versus your secondary. Faster versus slower. Very slow here, and extremely slow here. So very slow here on your primary. It's a primary, but still it's going to be this is your neopentyl case that we had before. Very slow, because even though it's a primary, it is still going to be a lot of aggravation in terms of sterics. And extremely slow here to non-existent is your tertiary position, right? But SN2 reactions do not happen, do not happen on a tertiary substrate. Period. End of statement. All right. Okay. And again, there's no reactions on a vinylic or on an acetylenic carbon here, or on a phenylic carbon there at all. You can't have this sort of displacement here, because you can't get behind it in order to be able to overcome. You can get behind this carbon, but you can't overcome the strength of the sigma and the pi bond of any of these species over here. And in this case here, you have 2 pi bonds and 1 sigma, so it's just really going to be totally non-reactive. Now, SN1 is sort of the exact opposite. The order of reactivity for an SN1 is like super awesome. Here you have a tertiary is the most reactive, secondary is the next most reactive, primary you don't form any carbocation, and then methyl, right? You can't have, because you can't have you effectively cannot have a primary, a methyl carbocation. So the more stable the carbocation formed, the faster the SN1 reaction. Notice how this is almost exactly opposite of your SN2 reaction, okay? And here's your stability of carbocations and so forth and so on. But here's the one thing though, right? So here's our thing that we had from before about showing you the stability of carbocations. But there is here the allylic halides here and benzylic halides undergo SN1 reactions at reasonable rates. This guy here is a primary species, as this benzylic is here. And so remember how we talked about, when we talk about organic chemistry or even science in general, there are no absolutes. There is no black, there is no white, there is no ones or zeros. It's sort of a continuum, right? And so here you have things here that have a lot of qualities of an SN1 reaction, but they look like they might be an SN2 reaction, okay? And so there's lots of, so here for allylic halides, if you have a strong nucleophile, it will act more like an SN2 reaction. But if you have a gentle nucleophile or a weak nucleophile, it will give you a lot of SN1 type of qualities. So you might see, for example, if you have an allylic situation and the appropriate solvent in a weak enough nucleophile, you actually might have, if you have some stereochemistry there, you might have some mixing of stereochemistry, something that you would not have if you had an SN2 reaction. But if you have an SN1 reaction, you would expect, if the reaction center is also a stereocenter, you would expect to have some sort of racemization, right? If you have an SN1 situation, all right. So you can have so both allylics and benzylic can undergo SN1 and SN2 reactions as substrates. It just depends on your species. It depends on your nucleophiles. If you have weak nucleophiles, these guys here will be more SN1 like. If you have strong nucleophiles, they'll be more SN2 like. Okay. And the reason for that is, of course, some resins that we've already talked about. So the effect of the concentration and the strength of the nucleophile for an SN1 reaction is just going to be the rate. The rate will just be dependent on just the substrate concentration itself. It does not, but the nucleophile concentration does not participate in the rate determining step. All right. The rate of an SN1 reactions are not affected by either the concentration or the identity of the nucleophile. So don't worry about the nucleophile. Just worry about the concentration of your substrate. The thing that's acted upon, the electrophile, to worry about your rate of reaction. Okay. For SN2 reaction, of course, both the concentration depends on nucleophile and substrate, as we talked about before. Hence the 2 in the SN2. It's a bimolecular nucleophilic substitution. All right. Identity of a nucleophile. Okay. Notice how we're calling these things a nucleophile now. we name these things very conveniently for us. We name them based on their employment. In the case here, we have a good nucleophile here, which you can also see is a good base. If you really look at it, right, it could be a good base. And so that's sort of how we look at things, as good bases and good acids if we're talking about acid-base reaction, but good about nucleophiles if we're talking about substitution reactions. All right, so here we have a good nucleophile here, right? The relative strength of a nucleophile, its nucleophilicity, is measured in terms of the relative rate of the reactions of SN2. So here, this guy here, this methoxy here, with treating that with methyl iodide, will give you the rapid reaction of the formation of this methyl ether. If you have methanol, which is just like the conjugate acid version of this, you have this under the same exact reaction will give you the same exact product, except it'll be very slow, right? Because it is a poor nucleophile. It is not nucleophilic enough. There's no impetus. So this CH3O- has the impetus, has the drive, has the energy to slam into the backside of this carbon in the methyl iodide to give you your ether. This methanol here is pretty happy. It's neutral already. It doesn't require a lot of stabilization, from anything else. So it'll be like, yeah, I'll crush into the backside of this methyl iodide here, but only to give me a change of pace, to change some scenery. But there's no overarching need for it. Yeah, this is a partial negative in the oxygen and a partial positive in the carbon iodine bond here, but it's still doesn't have the urgency, right, of a good alkoxide nucleophile. All right, and so the strength of a nucleophile can be correlated with 3 structural features, sort of. So, and I wish it was this simple, but it's not. It's not this simple. But these are a good place to start. The relative charge, a negatively charged nucleophile is always more reactive than a nucleophile than its conjugate acid. So, for example, hydroxide, HO- is better nucleophile than H2O, its conjugate acid. RO-, the alkoxide there, is better than ROH. So like methoxide is better than methanol, for example. Okay? So that's the one thing. So minus is better than neutral. And of course much better than positive. Positive are not nucleophiles. In a group of nucleophiles in which the nucleophile atom is the same, nucleophilicity is parallel basicities. Okay? So you can use sort of your your pKa table as sort of a list of good and bad nucleophiles. So alkoxide is better than hydroxide, which is way better than this acid, than these carboxylate, right? Notice minus, minus, minus. Now we're getting into neutral. This carboxylate is way better than alcohol, which is much better than water. All right. So you can sort of use your pKa table in terms of your to get a good idea about what's a good nucleophile. All right. And then lastly, when the nucleophile atoms are different, then nucleophilicity may not parallel basicities. Okay, so in product solvents, the thiol, the cyano, and the iodine are all weaker bases than hydroxyls. Yet they are stronger nucleophiles than hydroxide, right? So they're all weaker bases than that, but they're all stronger nucleophiles than hydroxide. All right, so that is just what that means. All right. So when they're all different, you can't really you're going to have a hard time being able to compare them. All right, that's what sort of this is saying. All right. So and this only sort of goes for product solvents. There's also one thing that your book does not talk about, which is I think super important. All right. It's this, and I'm going to draw real quick here. Okay, yeah, let's just do this. This guy here, this guy here, H3CO-. So methoxide is a better nucleophile than isopropoxide. Why? The simple case of size. This guy here, now remember, in science, we name things by their employment. So while these guys here might be like similar in terms of bases, like in terms of like methoxide and isopropoxide are what, both what, like 16, 17 pKa units? Big deal. But methoxide is a better nucleophile than isopropoxide. Why? Because this guy here is smaller. This guy here is smaller, and it does its job better. Because imagine trying to throw it. Imagine this, right? I'm going to erase it again. Imagine taking your R group here. Your R group here can be either methyl or isopropyl. Take this guy here and react it with, this random compound. I'll just put this. I'll make this a stereocenter with this random bromobutane. All right, and then the appropriate solvent DMSO, for example. We'll learn about that next. This guy here has to. This alkoxide here has to be able to squeeze in between that CH2 and that CH3 to kick off that bromine. What's going to do better at that job? The small lean, methyl guy, the methoxy guy, or the isopropoxy guy, which is a lot bigger because it has, essentially it has a secondary carbon on it. This guy here is a methyl carbon versus a secondary carbon on it. Who's going to win is going to be your. Sorry, I'm not going to make the mistake I made last time. I'm going to do it the right way, right? The thing that I will form, that will be the thing that will be the most populous, will be the R methyl. Why? Because it is a smaller nucleophile, which means it's faster and it's better at its job. That's exactly what it means, right? It just is a small thing. So in terms of, nucleophilic atoms are different than nucleophiles, may not parallel basicities. That's all well and good. That means you have to be able to compare something that's within a trend, right? That's within a similar set of structural features. But they don't talk about the size, and size here matters. The best nucleophiles are small, hard, and compact. What do I mean by a hard nucleophile? I mean that the negative charge is a localized charge, right? As opposed to a soft nucleophile where the minus charge is distributed over like 3 atoms in the case of carboxylate, which is why carboxylate is not a wonderful nucleophile. It exists and it happens and it works, but it's not fantastic at all. Okay? So size. So that's the fourth thing I want you to know. All right? There's that. All right. So SN2 reactions are favored by polar aprotic solvents. Aprotic just means you don't have a proton on them. So like, methanol, water, and ethanol have the OH group, and that hydrogen is technically a proton. You could be abstracted. You could abstract that proton. But in general, reactions are favored by polar aprotic solvents for SN2s, acetone, DMF, or DMSO. In general, SN1 reactions are favored by polar protic solvents like ethanol, methanol, and water. In general, I'm not talking about specifically, I'm saying but in general, okay? There are some specific cases where you don't have that feature, okay? All right. So classifications of solvents, polar versus nonpolar, and this is you could read this too. We'll care more about these for every new reaction that we've learned. We will determine what the appropriate solvent is for the substrate. It's a lot more than just this little graph or just these little words. It's a lot more than just that. Okay. Polar aprotic solvents have strong dipoles, but no OH or NH groups here, like DMSO, DMF, hexamethyl phosphoramide, HMPA, or acetonitrile. Again, all non-protic or aprotic solvents. Okay. Polar aprotic solvents tend to solvate metal ions, and what it means by solvate metal ions is that the DMSO will help to associate with the sodium in the case of sodium methoxide, to help pull it away from the oxygen part of the methoxide to make it a naked anion. What do we mean by naked anions? A naked anion means that it is an anion in the case here of an O minus here, that the sodium has been stripped away from it. When that happens, that makes the anion here more reactive. If you have a sodium that's very close to this alkoxide, it is stabilizing that alkoxide, and it will make it less nucleophilic. If you use like DMSO or DMF, those solvents will help to dissociate the O minus and the Na plus in the case here, and separate them to make this guy here a naked anion, to make this guy here even stronger. So it will not be as stabilized. You don't want to stabilize a good nucleophile or a good base, because then you are masking some of its ability to do its job, right? So you don't want to do that. You want to strip it away to make it be reactive. Okay. All right, and then here's some relative rates to convince you of this data, right? So tremendous acceleration in the SN2 reactions with polar aprotic solvent. So if you use a polar protic solvent, your rate is 1. But if you use DMF, or even DMSO probably, you'll get 10 to the 6 times faster using a polar aprotic solvent in DMF, to give you this data over here too. So there's your data just to prove it to you. All right. In polar protic solvents, the nucleophile here is solvated by the surrounding protic solvent, which makes the electron pair of the nucleophile less available, right? So if you have a minus charge here, the partial positive charges of all your hydrogens, if you use a polar protic solvent, will mask the nucleophile's ability to do its job, right? Because the nucleophile is like, all I want is some positive, and it wants to get that positive by attacking an electrophilic carbon or something that's electrophilic. But if you have a bunch of hydroxyls around, in the case here you have ROH, right? These hydrogens here are all partial positive. So these partial positives will sort of surround that nucleophile and say, hey, I imagine that this is ethanol. Hey, you want a drink? 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 It's offering it drinks. It's like, all right, I'll have a drink. And it won't do its job because it'll be drunk with protons. So I said that's something, all right? And in the case here, it sort of makes sense. This guy here is being quenched by the beautifulness of all these protons here, but that's not good for its job. It can't do its job well if it is drunk on protons. So let's leave that. Let's just leave that metaphor where it is and go on. All right. Okay. Halide nucleophilicity in protic solvents. And in the case here, you have, let me see. So iodine here, so you have fluorine here and iodine, and you have some solvation issues here, right? So let's say you have iodine, bromine, chlorine, or fluorine, right? If you take alcohols and you throw in these ions, you can have things here that can be solvated to a certain extent, and sometimes you might want to have that, or sometimes you don't want to have it, right? But you want to be able to control this effect, all right? And it has a lot to do, believe it or not, a lot of chemistry has to do with just size and, just basic things you may have learned from playing with like Legos, right? Just like making models of things. The fluoride here is strongly solvated, right? Why is that? Because you have more ability, right? You have more ability for the hydrogens to surround this guy here, right? Because there's more room for this guy here to surround, each hydrogen here to surround this fluorine here, right? And so just in terms of size, this guy here has more space for this guy here to be able to surround this fluorine here, hence solvating it. All right, and it's opposite with this iodine. You have a weakly solvation issue here because now you have a larger, more diffuse ion here, and there's not going to be the concentration of negative charge around this iodine for it to really matter for those protons to get at, right? So this ball of electron density is less strong. It's less of it has less electron density around it for these hydrogens to care about stabilizing it because of its electronegativity. This guy here has more electronegativity, so there's more reason for these guys here to say, hey, I want some of that negative charge there because I am a positive thing, and it wants to be attracted to it. All right. So iodine here is a stronger nucleophile in protic solvents, as its electron pair is more available to attack the substrate in the SN2 position. Why is it more available? Because it is weakly solvated in a protic solvent if you want to go that route, right? And if you don't want to go that route, then don't. But you can do some SN2 reactions in polar protic solvents. It's not the best choice, but you can get away with it sometimes, which is why I'm saying, like, there's, you know, in only in the case where I'm describing always and never, like, you can never say never in chemistry because there's always an exception that you'd want to use that one specific scenario. All right. All right. So solvent plays an important role with SN1 reactions, more so than with SN2 reactions. The SN2 reaction solvents are just the role of the solvent is in the SN2 is just to get sort of out of the way. SN1 is where you need help with, you know, liberating a leaving group and so forth and so on. But SN2, no, the SN2 just has, you know, the job is the nucleophile's job to attack into an electrophile and kick off the leaving group here. But in SN1, yes, you have the ability there to, you know, for solvents to help out along the way. All right. So polar protic solvents here stabilize the development of a transition state. So there's your rate determining step there, right? And this guy here is liberating a chlorine to give you this species over here, right? To give you this, you know, this transition state here is potentially forming this tertiary carbocation, and it's doing it because several moles of the alcohol solvent, for example, in an SN1, is helping to liberate that chlorine. And when that happens, you then end up forming this partial positive charge here, which then ends up turning into a full positive charge in the tertiary carbocation. All right, so the solvent here helps the role, helps the role of the leaving group to leave. All right, and the leaving groups again leave with the electron pair that was used to bond to that group, which is why you get the alternating charges there. All right, so the better species that can stabilize a negative charge, the better the leaving group in an SN2 reaction. All right, so for an SN1 reaction, you want this. You want this thing to occur because you want to form this, right? But in an SN2 reaction, you have no such luck. In an SN2 reaction, the nucleophile here comes in, slams into the backside of that carbon, kicks off that X, whatever that X is, could be a halide, could be a tosyl, could be some other thing, and it gives you your new bond that you formed there, right? And so this guy here is sort of the best case scenario for an SN2 reaction. So here there's no real role for the solvent in an SN2 reaction. The solvent's role is just to get both things into solution and get the hell out of the way. An SN1 reaction, yep, please help pull off that leaving group, and that is the important part of that. All right. So here is an example of and we talked about this before in a slightly different sense here, but the examples of reactivity in an SN2 reaction here. Here's your methoxide. Here's your halide, and then here's your alkyl halide in terms of your electronegativity, in terms of your electrophile, and then here's your methyl ether that you're forming here. So your relative rate in terms of leaving groups now we're not talking about this in terms of nucleophiles. We're talking about this in terms of leaving groups. So we are fixing our nucleophile, which is going to be our methoxy, but now we are varying our leaving groups. This is different than the previous slide because we were varying the nucleophiles, and here we are not. We are just varying the leaving groups. So the best is a tosylate. Why? Well, in this case here, it's because of the resonance formed after tosylate is liberated. Iodine, bromine, chlorine, iodine, bromine, and chlorine are the best leaving groups of the halides because they have a large diffuse electron density around their nucleus, and they are easily stabilized by solvents, right? But the worst leaving groups here are things that are like very strong bases. So if you see a hydroxide, terrible leaving group, or an NH2- or an RO-, Again, all horrible leaving groups. You'll see, like anything that you see in your table that's like above, oh geez, I don't even know. It's above, HF, the HF, pKa unit. This is going to probably be a pretty terrible leaving group. And I say terrible leaving group based on a limited set of experiments. Hydroxide might be a fantastic leaving group if your solvent is hydroxide. But if your solvent is water, you will not have hydroxide leave as a leaving group. You can have any of these other guys here leave, but as if you're in water, none of these guys here will leave at all. Period. Right? You have to have something that wants to be stabilized by your solvent, and these guys here are all stabilized. This guy here is stabilized because of resonance, and these guys here are stabilized for other reasons associated with their large diffuse electron cloud around their nucleus. All right. So normally RF, ROH, and RNH2 or ethers do not undergo SN2 reactions, but we will encounter examples where they will be part of the reactivity. Okay. And so here's like a sort of an overall little cartoon of it, right? If you have hydroxide here, then if you have ROH here, you're going to have OH here as a leaving group, and that's going to be a strongly basic anion. That's going to be a higher energy species that will not want to form. Unless this nucleophile here is ridiculously stronger than hydroxyl, then that might happen. But then you'll have other competing chemistries that might occur as well, including deprotonation. So you got to sort of be careful. But if you have a good leaving group here, something that has like an oxygen that has a positive charge, because oxygen does not want to have a positive charge, and you have a decent leaving, and you have a decent nucleophile here that will attack the backside of that carbon. Now all of a sudden you have a weak base here as your leaving group that has left, and you have your new compound here with your nucleophile already attached. But here, once you have the backside attack of this carbon from that nucleophile, if you have a good leaving group, something here that wants to break this RO bond here. In the case here, this wants to break because that oxygen is the second most electronegative element on the periodic table. It absolutely does not want, right, to be a positive charge. So it's fine. It will leave this RO bond here will break, and then you'll form your good leaving group, which is going to be your weak base of water. Okay. Right, and here's some other things here that are also very good leaving groups here, and these are all good leaving groups for pretty much the same reason, and that reason is resonance. You have nice resonance between this oxygen here and that sulfur and these other oxygens here as well, and that goes throughout the entire series. So that is the reason there. Okay. Functional group transformations using SN2 reactions. So you can, pretty much. This is how we should start thinking about organic reactions now. Think about the substrate, and not just think about the one nucleophile. Think about all things that you can possibly do with these things, right? So here you have 1, 2, 3, 4. You have N-bromobutane, and if you hit it with a hydroxyl or a cyano or a methoxy or a thio or a methylthio, right? You can get all these different derivatives of this bromobutane species, right? And and from here you can do additional chemistries on these substrates here to do further chemistry after that. And that's the thing that we'll be focusing on our next exam, the actual synthesis of molecules using these very simple SN1 and SN2 type of techniques. All right, and here's even further examples that are a little bit more complicated, but you can still see where you have the same type of things here. You have iodine coming in, displacing that bromine here, giving you your iodobutane. Or you have this acetylene unit here that comes in and does an SN2 reaction to the backside of that carbon over there. Or even this terrible nucleophile over here, this acetate, terrible nucleophile. Unless you have a really good leaving group on a really unhindered substrate, then it sort of works out a little bit, okay? And then azide, and which is a more advanced anion, and then even trimethylamine has a lone pair here that can be nucleophilic. All right, so there's lots of good examples, and here's even further examples. Notice that you can that you have a wide range of control. Don't be fooled by this pretend stereocenter. This is not a real stereocenter. This, even though it's sort of inverted as they drew this, as the publishers drew this slide, there's no stereocenter to this. So it doesn't make sense. But what they try to tell you, from this is that this is an SN2 reaction. So inversion, like the methyl thiol comes from the back side, from behind the screen here, and attacks to the back side of that carbon, and then has that iodine here leave to give you this overall species here. That does happen, but there's just no stereochemical evidence for it because it's not a stereocenter. All right. And so here's this. Here's sort of a tricky question. How do you go from this iodobutane to the cyanobutane after the active, which is also chiral? And again, the twin of the chiral molecule here. What do you need? You need an actual reaction to stereochemistry. But if we just hit it once with a cyanide group here on that, and there, we only have inversion configuration. We need overall retention configuration. How do you do that? Well, by something called double inversion. What you think? Two SN2 reactions being done back to back. All right. So let's do our first thing. We'll take this iodine here, and we'll attack it with sodium bromide, and that will give us our SN2 reaction with this. So you go from this chiral molecule here to this other chiral molecule here through an SN2 reaction. It is a direct stereoselective reaction. Right? I'm sorry, stereospecific reaction. It'll go specifically from this one stereocenter to this other stereocenter. And then to go back to this stereochemistry wherein you have something that's coming out at you, you can just hit it with something else, like the ultimate thing that you want, which maybe is the cyanide group here. So you just throw in sodium cyanide and DMSO, and there you have it. You have your sodium cyanide, you have your 4-cyanobutane. That is a chiral molecule. Okay, it's going to be your 1, 2, 3. It'll be your R-cyano bromobutane, right? So it's not too bad. Again, these vinyls and phenyls here do not react at all. So period, end of statement. So don't even worry about those. All right, and here's some examples that don't work. I don't know why your publisher wants to talk to you about this, but there's that. And here's now something that is like we might stop here pretty soon because I don't want to. This is a big deal, and there's lots of things to draw here. Okay, but let's just start off a little bit. Okay, hand in hand with substitution is something called is called elimination. There's a sort of a neighboring reaction called elimination, and the conditions for elimination are eerily similar to substitution. All right. In the case here, you have this methoxy, which acts like a nucleophile. This attacks the backside of that carbon, kicking off that bromide there, giving you this species over here, which is something that we just talked about, and we began talking about last time. So there is that. Pardon me. So there is that ether. But there's something else called elimination, where methoxy is now acting true to its form. It says, hey, I'm originally a base, not a nucleophile. So then bases do what they do. It will abstract a proton, and then that proton will release the bond from a neighboring carbon here that will snap on down, and then have that bromine here snap on out to give you your acetylene species. All right? I'm sorry, your ethylene species. And that is through the process of elimination. All right? Now, elimination is something that is always in competition with your substitution process. All right? And so that is going to be a problem that we have to constantly deal with. All right? And so here we have the case here, we have this iodopropane here, and if we hit it with terbutoxide here will give you 15% of the SN2 reaction, but 85% of the elimination process. And there's a simple reason for that. Remember when I said that fourth phantom point about the nucleophiles? They have to be small. They should be small to do their job well, to sneak in behind the carbon and kick off the leaving group here. In this case here, terbutoxide is jagunda. It is huge. There's no reason, that you shouldn't have a nucleophile this big, except to teach you about why nucleophiles shouldn't be this big. And here's the reason for it, right? Because you only have 15% of substitution versus 85% of elimination. It would rather, the tributoxin would rather yank off the proton that's on an adjacent carbon to that leaving group than attack the backside of that carbon over there, right? So it's just because it's easier to do so. It's just easier. It's more favorable for all species involved. You can favor it, but for the most part, it's going to be, more likely to form the to form the eliminated product. All right. One thing we have to know how to identify here is the locations of these important species to do this chemistry, right? In the case here, this is the protons to be abstracted or pulled must be beta hydrogens. Beta means, so here's the alpha carbon. The alpha is the thing that has the leaving group on it. Right next to it is a beta carbon, and that beta carbon here should have beta hydrogens on it. If it has no beta hydrogens, you cannot do elimination, right? Elimination only is you need to have beta hydrogens to do a dehydrohalogenation, which means to eliminate a hydrogen and eliminate a halogen. So dehydrohalogenation is a fancy schmancy sciencey word for beta elimination, where you are pulling off a beta proton and you are eliminating a halide. So once you pull off that proton here, this lone pair here, this bond pair snaps on down and kicks off that halide. All right, and when you do that, in the case here of isopropyl bromide and tributoxide and tributanol, you end up getting this propene species plus KBr. Because why KBr? Because potassium here plus that bromine there is your KBr, plus your tributanol. Your hydrogen from tributanol comes from that hydrogen right there, and that is why that happens. All right. And you know what? Let's just stop here. There's only a few slides left. I'm going to finish this up with you on next time I see you, and I want to talk about some carbocation structure, and also I want to finish up this elimination thing from this chapter, and then we will head into chapter 7. All right. Thanks for your time and attention, folks. Sorry I couldn't be there today, and I will talk to you soon. Thanks. Bye-bye.